Hello and welcome to the second video in our lecture on user authentication with passwords and biometrics. In this video, we're starting to focus on passwords, which, as you know, is used pretty much by every network-based system, web-based e-commerce site, and so on and so forth, as you've been using them essentially every day. So the idea of a password is that you own a password that only you know, and then you submit it to a system that compares this password to the recorded password they have in their system password file. And then if there's a match, then you're considered authenticated. So again, this is the second step in the access control process. And once you're authenticated, then you can go through the authorization stage and given some privileges with respect to information or computer systems or computer services. So the question is, why are passwords so popular? Um, as you already know, they are probably not always that secure, but they are definitely one of the most popular user authentication systems. So why are they so popular? Well, first of all, passwords are essentially free because it's something that you know. It doesn't cost a lot of money for you to create one and for someone to check it. So they are definitely much cheaper than other options like biometrics that we're going to talk about later. So that's really one main reason. And of course, the other one is convenience. So, in particular, in situations where your password is compromised, it's definitely much more convenient for a system administrator to just reset your password or even have an automated reset system. Consider the alternative if you were using a fingerprint biometric system, then what happens when your thumb is compromised? Not so easy to replace as a password. So, the way this works again is that the system contains a password file that will contain the list of all the passwords for the users that have access to the system. And so, how can the authenticator verify that you entered the correct password? Well, it must know this password and again be stored with this file. So, obviously, it sounds like a pretty bad idea to store all of the users' passwords in a file. So, this is not really the way that it should be done. So, the solution, of course, is to use hashing. So now that we've discussed some cryptographically secure hash functions, you could see how this would be a useful mechanism to handle passwords. So basically, the idea is that you take your password, you run it through a hash function, which then gives you a hash code. And the idea is that two different passwords should not hash to the same hash code as long as the hash function is collision resistant. And of course, it's for you to make the right choice for the hash function. So doing this is very easy. As we talked about, hashing is much faster than encryption and fast as well. So of course, the problem is, what if the attacker truly gets a copy of the password file? Remember, there's a single file within the system that will contain all of the user's passwords. So it must be protected against attackers. And what if the attacker is able to obtain this file? Well, in this case, of course, with the file containing only the hash codes of the users, then the passwords are still protected in some sense. So how does the system check your password or performs the user authentication step? Well, it's just after you enter your password, the system can just hash it and compare the hash code it obtains with whatever is stored in the password file. Now, of course, there's other possible ways for Trudy to attack this system. And one of such attack is called the forward search attack. And so the idea is that if she obtains the password file, she can perform this attack offline. So what that means is she can take hours and days to do some computation once she obtains the password file, and then she can use the outcome of that attack later on. So the way the attack works is pretty simple. If the intruder can actually go through all the possible passwords, or at least the likely passwords, so P1, P2, P3, and so on. And then all the attacker has to do is to hash each one of these passwords to get a hash code, H1, H2, and H3, and so on and so forth. And then all the attacker has to do, quote unquote, is to compare every one of these hash codes to the hash codes stored in the password file that the attacker obtained. And of course, if one of those hash codes that are computed by Trudy in the forward search matches one of the hash codes in the password file, then she can infer that the password of that user was the one that she computed the hash code for during a forward attack. So that's called a forward attack because remember that the the main property, or one of the main properties of a hash function, is that it is pre-image resistant. That means given the hash code, you're not able to go back to find the password that was fed as input to the hash function. So this is going backward. But in a forward search, Trudy does not have to go backward. She can go forward from a guessed password to the hash code. So there's no difficulty there. She just has to try a lot of them since she doesn't know what the actual password is. So before we move forward, let's make sure we compare these passwords to the keys that we've been using in the cryptographic primitives we've been discussing. Remember that a cryptographic key is basically a bit string, and a password is typically a sequence of characters. So to compare things, equal to equal. Let's say we take a pretty short key, only 64 bits, which is, very short these days. So it's not considered a secure key at this point, but for the sake of example, let's use that. And similarly, let's look at all the possible passwords of 8 characters. And the reason I picked those numbers is because we're going to compare the size of the key spaces, and we're going to notice that they are the same in both cases. So clearly, if you have 64-bit keys, you have 2 to the 64 possible cryptographic keys in this column. Now, how many possible passwords do we have here? Well, we have 256 characters, say, in 8-bit ASCII, and we have 8 characters. So we have approximately 256 to the 8 passwords. I say approximately because if the system allows fewer than 8 characters, then you have a few more passwords, but let's not worry about those. And this number, of course, is equal to, let's see, 256 is 2 to the power 8. And we're going to raise that to the power 8. And so what is 2 to the power 8 raised to the power 8? Well, it's also 2 to the 64. So again, we just took these arbitrary numbers here that are somewhat reasonable, at least for passwords, a little bit too low for cryptographic keys. And in this case, the two key spaces have the same size. So again, we're trying to compare the security of these two mechanisms. And the key point here to take away is that the way that cryptographic keys are chosen is completely at random. In fact, as we discussed in a previous lecture, these keys are chosen automatically by some pseudo random number generator algorithm and so on and so forth. On the other hand, the way that passwords are chosen are typically, at least in many cases, um, done in different ways. In fact, usually the user gets to choose the password. And so how do users choose password? Well, they usually don't choose random characters. They pick passwords that are reasonably easy to remember. And so what does that mean? Well, that means that if an attacker is trying to break such a system, then in the case of a cryptographic key, they would have to do a, say, exhaustive search, which is 2 to the n minus 1, so 2 to the 63 amount of work. And notice this is approximately equal to 10 to the 19, which is a very big number. This is a number of keys that the attacker would have to try through a brute force search. On the other hand, though, even though we have the same key space for the set of possible passwords, because users don't pick random passwords, but pick usually actual words or pieces of information that pertain to themselves, the number of passwords that you should consider first are much less than 2 to the 63. Let's say maybe a few millions, or maybe even billions. But the point to realize is that if you do an exhaustive search, or quote unquote exhaustive search, on common passwords, the set of passwords you have to check is much smaller than what you would have to check on a randomly generated key. And remember, this number is actually way smaller than what is actually used. So the key space in the case of cryptographic keys is way, way bigger than this. And therefore, even just from a pure brute force search or exhaustive search aspect, cryptographic keys are much, much safer than passwords. Nevertheless, passwords are used a lot still to this day, so we're going to spend a good chunk of this lecture discussing how those password-based systems work.